about the storage system. Okay. So I'm going to talk about what's new in HDFS and some of the future development, what's coming out in Release 2, and some of the future development we are working on. My name is Sanjay Radia. I work at Hortonworks. I'm one of the founders at Hortonworks. Previously, I was at Yahoo as part of the team that actually built Hadoop. My team wrote about 80% of the code. I was the chief architect of Hadoop core at Yahoo. Prior to that, I was at Sun Microsystems and another startup, worked on various technologies. And previous to that, I'm from Canada, with PhD from University of Waterloo. So I'm going to talk a little bit about what's coming new in the Hadoop 2 release, federation, high availability, snapshots. And then I'm going to start talking about some of the other major architectural directions that we have started to make and how it's going to shape Hadoop going forward. Okay. So to give you a very quick overview, Hadoop is really about scaling I/O, scaling storage, scaling CPU. And the idea is that you add commodity servers and JBODs. JBODs being, disk without RAID controllers. And typically you have, you can have clusters as large as about 6K nodes, okay, 6,000 nodes, okay, and about 120 petabytes in a single cluster is typically what's been measured at for example, Yahoo has a cluster and Facebook has clusters that are close to these sizes in storage, okay. The main idea in kind of Hadoop is that the row system is fault tolerant and very easy to manage. It is built-in redundancy for storage. It can tolerate disk failures, node failures, and can automatically manage addition, removal of nodes. If you want to add or remove nodes, you can do it in a live system. Okay, and typically, if you have somebody who is reasonably experienced in managing Hadoop, you can actually manage 3,000 to 4,000 nodes with a single operator. Okay, and that is because the system manages itself. You really only have to manage one of the master nodes and the so-called data nodes. I'll explain to you what that means. Okay. The other kind of unique feature that comes because of Hadoop is that storage servers are not just used to store the disk blocks, but they're also used for computation. And the general idea in Hadoop traditionally is to move computation to the data. Okay, and the file system is not a SAN, but it's a high bandwidth network access via Ethernet. Okay, and it's a scalable file system that has read, write, rename, append, but it has no random writes. Okay, very quick overview of the system in case some of you haven't seen here. What I have showed over here are the two layers in Hadoop. There's a namespace layer and there's a block storage layer. Okay, on the top, so the namespace layer has a master node called the NameNode. It stores the namespace actually fully in memory today, and stores this, persists the state on local disk or NFS. And I'll show you what the HA architecture looks like. And so it's a hierarchical namespace that maps from file names to block IDs. And at the bottom, what you have is a set of data nodes. They contain blocks which are replicated. And basically, periodically, they send heartbeats and block reports. And then the block map basically gives you mapping between the block ID and the block storage. Clients actually access the data directly. So for example, they'll do a namespace operation then, and then they will do the read directly from one of the locations, the location that is closer to the client. And the write, similarly, they'll do an open to figure out which location, right, and then the write is written as a pipeline. Okay, so typically the default in Hadoop is 3 replicas. Okay. The system also is periodically checking the system. So for example, it's checking the blocks to see the checksums are correct, okay? And so for example, if you find in this particular case that this block is bad, either because the checksum shows or the disk disappeared, then the name node is notified and he arranges for the block to be replicated. The same thing actually occurs if had a missing a data node that dies. Often a question people ask when we ask them to install Hadoop, they say, why I don't want 3 replicas, I'm going to put RAID because I'll get more efficiency. And one of the things here is that because it's not using RAID, it can actually do recovery of nodes or disks. In fact, this is, in my view, the single kind of new thing that the Google file system did. Prior to the Google file system, there were several systems that had a master node and a set of data nodes that talked about horizontally scaling the storage. So basically, the idea is as you add data nodes, you scale the I/O, you scale the I/O bandwidth, you scale the storage. So this architecture is being used quite heavily in many, many systems. And the main thing that the Google file system did was actually not to use RAID on the local disk, which basically meant that the recovery of disk failure, node failures, etc., is extremely, extremely fast. Okay? So for example, if you had a RAID system, if you lose a terabyte, you're looking at 24 hours, or something in the order of that, 16 to 24 hours. In Hadoop, you can actually recover very, very rapidly. Okay? You can recover extremely fast. I'll give you a number in one of the slides. So Hadoop 2 really has a number of improvements. It has append, it has improved scalability, performance, and a number of features. Okay. Over the last year, there's been actually, this number is slightly off. It's over 2,500 new commits in the open source community. So it's been a very extreme, over 350 to 400 lines of new code in HDFS and Common, which is the common library that Hadoop uses. Okay. So when I kind of look on, as we make improvements, and just do a quick recap of what were some of the things that we did in the past that we kind of carry forward and the things that we are changing. So one of the early choices was that on the storage nodes that I showed you on the bottom, we do not write directly to the disk. We actually use the underlying file system, and that could be, a Linux file system or a Windows file system. And then even in Linux, you have a choice of which one. So that's actually made the system extremely reliable. That in a period of 5 years, since about 2006, about 7 years, the system has been extremely reliable. It's been in production use over the last 3-4 years, 5 years. Okay, and part of it is that we did not build our storage system our block storage system from scratch. It also gives us the advantage that we can move from ext3 to 4. It also helped us work on Windows very easily because there was a system over there. The other one was the fault tolerance, the active monitoring, the replication, there was such thing. And the other one was the NameNode master kept the whole namespace in memory. That has worked out very well, and that is something we are going to be changing. Okay. There was a study we did in 2009, 2010, where we had about 7 nines of data reliability. And that was actually the worst we've had. We lost about 19 blocks out of 320 million blocks. And those were due to bugs, were released 0.20. And those were fixed within about a month or so after we deployed at Yahoo. And since then, we haven't seen we'll be doing another study. So it kind of rivals storage systems from makers like EMC. And about 0.58 failures of the master node in about 25 clusters at Yahoo. Okay. As I mentioned, it recovers from disk failures. I think I covered most of this. The largest clusters are about 120 petabytes, and right now there are about 60,000 nodes of HDFS in deployment around the world. Okay. So we look at now the changes that we've made. And the foremost thing was that the storage system originally in Hadoop was dedicated to serving only the name node. In fact, serving only a single name node. So although the system was kind of led to have block storage separate, the code was not quite that architecture. So one of the big changes we made was to make the storage block service. Okay, by blocks I don't mean row sectors. These are what I call HDFS blocks, so they kind of range from, typically at about 128 megabytes to, 50 megabytes to about, 256 megabytes. And we made that service completely general. So for example, you can go and create your own pool of blocks for your own service. And the first benefit that we got out of that was rather than have one HDFS namespace, we can have multiple HDFS namespaces. okay? That gives you the scalability, but it also meant that, for example, some customers we found that they want to use 2 independent namespaces in the same cluster or multiple, and the main kind of often a reason for that is you have a production system and you have ad hoc researchers who are doing analytics and they're writing new programs submitted. And typically, for example, at many places, Yahoo, Facebook used to keep these kind of systems separate, okay? Because people in the ad hoc queries often write programs that can actually put a lot of node on the master name node. They can do stupid things like create a directory with 2 million entries in it in a single directory, okay? And so now you have an option of sharing the storage system, storage cluster running multiple independent, running production and non-production together if they wanted to. Okay, there is actually a startup that is looking at using this model to kind of have a shared storage. They're providing Hadoop as a service and using the same low-level storage system, and then using independent volumes for each of their customers. Okay. The other one is that you can also start building new independent services. In fact, we have a intern from CMU who actually prototyped a file system on HDFS that only stores partial namespace in memory. She's actually a student of Garth Gibson, one of the creators of Raid. And that was actually fairly easy to do because, in fact, you can, she modified the HDFS namespace, but you can actually coexist in the same cluster with the older file system. And therefore, as you bring in new versions of a system, they can coexist. You can test them in production or test them as in the same cluster very easily. So it helps us do things like that much more easily. That before, once you bring the system out, it has to be rock solid, and so we can start having early versions being tested for various things in the same system that is in production. Okay, so there is something that's going to be coming out. The other kind of things is MapReduce uses its own temp storage, and HBase also uses HDFS directly, and now they can go and use the block storage system directly because they don't really need to use the HDFS namespace. Okay. The other thing that we are doing is to move the block storage management completely into the data nodes. Okay, I'll kind of explain that to you a little bit in the next slide. Okay, so this is kind of how the world looks under federation. What I have bottom is data nodes, so the disk kind of not represent physical disks, they represent nodes containing disks. Okay, and so each data node serves a set of block pools. You can think of a block pool like a LUN. Okay, not quite, but it is conceptually a little bit like a LUN. Each name node has one or more block pools, and the data node stores the block pools for all the services on the top. In this example, I've got a bunch of Hadoop namespaces, NS1 to NSK, and I might have a foreign namespace that decides to use the block pool. It may be a key value store, and it also can use the same underlying storage system. Okay, and so that's the general idea that currently in the block storage layer kind of contains of the physical storage and the management of the block. So for example, when you have a block that disappears because a node died, that management layer is part of the block layer. That management layer still runs today inside the name node. It's a library that runs inside the name node, and that's the library that we want to move further down. Okay, and then as I mentioned, now we're able to have multiple volumes. Okay, and to kind of show you how we manage multiple volumes. So one of the often people say, well, don't you need a global namespace? And so you kind of think about it a little bit. First of all, not always. Okay, like I mentioned, the example I gave you, sometimes you do want a private namespace. And the thing about global is that what does global really mean? The key is not the fact that the namespace is global. The fact is that you want to share. And the second thing it means is you want to share using the same set of names. Okay, a global namespace is actually one way to share. Okay, and what we have done is to actually provide a client-side mount table, where you can actually, if you like, mount all the various namespaces in a logical namespace. Like for example, you may have your 4 different name servers for data, project, home, and temp, and you could mount that and then use it. Now, if everybody does the same mount, then you have a global namespace. If everybody does slightly different mounts, let's say they all mount everything same except temp, then they have mostly a global namespace. Okay. Now, what you cannot do here is you cannot rename from here to here without, currently when you do the rename, you actually have to copy the data. We're looking at ways to do rename without that. But my own kind of philosophy here is that really, if you manage your namespace and volumes correctly, you really don't have to do that, okay? Building a truly distributed name node is very, very complex, where actually you can do renames across servers, and you kind of got to decide if that's where you want to spend the energy, okay? So for example, a lot of you probably have your home directory on an NFS server, and your colleague may not be on the same physical server, and you almost never notice the problem. Okay, but it is an interesting research area to do that. And in our case, the mount table is client-side, but you can also do a server-side mount table. Okay. Next thing, I'm going to talk a little bit about HA. So, you know, one of the things that was surprising for a lot of people is Hadoop did not have an HA system, you know, till about a year and a half ago. And why was that? It's because our name node was actually extremely reliable, okay, and is very reliable. In fact, I was talking to my colleague at LinkedIn where they run a Hadoop system, and I said, can you please beta test for us the Hadoop 2 version of HA? And he says, why? My name node fails only once every 1.5 years. I don't want to bother with an HA solution, because he knows that every time you have more software, you have more points of failures. But we did end up building this. So we actually have HA available in Hadoop 1. It is built using two tools called Linux HA or vSphere. You can use either of those. It depends upon shared storage. And it is a cold failover, so the failover times, let's say if you had about 100 to 200 nodes with about a petabyte, the failover times about 1 to 3 minutes, okay? In Hadoop 2, which is what I'm really going to describe to you guys, it doesn't require those solutions. You can still use them if you like, and does not require shared storage, okay? And basically, it's a hot standby, so the failover times are faster. So there's an, and we have something called full stack HA. Since that's kind of more about Hadoop as a whole, I won't kind of cover that in this talk because this is more about storage. But the main idea in full stack HA is that our libraries actually automatically retry whenever the name node is down, okay? As it fails over, it waits. The thing that is unique that we have done is that we have some key services that do wait, do check if the name node is down, and if the name node is down, they will start doing things like not go and kill a service that is spinning, or a job that is spinning, it will not go and kill it. Okay, so Hadoop often has jobs where if your job takes too long and you're making no progress on a particular, let's say a MapReduce job, it notices that. And so, for example, if your failover is taking too long, and normally failovers finish in very rapidly, but every once in a while you can have that happen. If you have, let's say, a split brain kind of failover that occurs. Another situation is, let's say the operator just wants to shut down the name node, an automatic pause occurs in the rest of the system. And so this is something that we have done. And when the failover finishes, you know, the system automatically goes back. Okay. So let me kind of describe what it looks like, the failover mechanism. So what I have here is the active name node and standby name node. Running on the same physical machine are two daemons on each of, so one daemon on each of them, called the failover controller. This is very much like the Linux HA daemon. It's a watchdog that watches the name node and is doing some commands like ls, does a ps command, various commands on the name node to see if it is responding to request. Right? It may be alive, but may be hung. It also checks the hardware to see if the NIC cards are fine, etc. It is in a kind of a leader election with the other one via Zookeeper. So they're doing a heartbeat via Zookeeper. Traditional systems, you know, for example, Linux HA or Veritas Cluster HA, the one that Sun used to have, the failover controllers communicate via each other via some sort of a heartbeat. Okay, and so that's how the failover occurs. Okay. The question, of course, the big change that occurred in Hadoop 2 was how does a standby read the state of the active? And we used to have a shared disk before. Now you can actually read through what we call quorum journal nodes. These are not separate physical nodes. These are daemons, and these daemons can reside on Zookeeper nodes or on the name nodes themselves and say the job tracker, and they use a Paxos protocol to keep the, and so what happens is standby is periodically reading the journal and keeping up to date. The second thing that has happened is that the data nodes are used to send, remember I mentioned you send block reports, now they send block reports to both the active and the standbys. Okay, and so the failover times becomes faster because of that. Okay. Moving on to the next thing is, sorry?
So you're doing a Paxos transaction for every namespace update?
Now it is actually going to the journal node, so what we do get is the batching. So even when we had a disk, right, a disk typically give you about 150 to 200 operations per second, and so our transactions are always batched. Okay, so whenever a thing gets sent out, you actually get not one transaction but many transactions, updates that happen. Okay, and we really haven't seen a performance slow down for that at all. One of the things that I think people often ask, I was talking to Garth about that, and he's really talking about saying that the active and the standby themselves are in a Paxos, so not like a classic HA failover. And there basically you would get a faster failover time. So right now, when the failover occurs, you typically have to wait 30 seconds or so before declaring something to be dead. Otherwise, you will get a false negative when, let's say, your traffic is very high, and then it's successfully failover, but you'll be wasting your time. Occasionally, that can occur. So that is something that people have talked about doing. Okay, and that would be interesting to see how much, whether that has any further. But on this particular one, we haven't seen any real, and that's because of the batching that happens on the transactions.
Yeah. Do you have how quickly can you create objects in the namespace? I mean, that's the classic benchmark, right? Can you do, because with a huge system, you want to be able to do like many thousands of new objects a second, right?
I haven't got the numbers on top of me, but I can get and mail that to you. Yeah, we are typically right now in Hadoop doing about 6,000 to 10,000 operations per second on a regular disk. In fact, Lynn, God's student, was measuring this with an SSD, and she was getting about 10,000. Okay, and that part of the code actually in Hadoop is not even that well optimized. Okay, we believe we could easily do something like 20,000 transactions per second. That's what updates. Sorry, that's what Zookeeper does. Zookeeper does about 20,000. Okay, so they kind of use a slight variation of Paxos. So the next other big thing is snapshots, and by snapshots really they're used you shouldn't think of snapshot as a backup because it's sitting on the same storage system. It's more like, again, accidental deletes. Most file systems offer that, like the NetApp Fire, for example, offers that. And so we've added snapshots. You can snapshot at any directory level. Okay, they're managed by the admin, so the admin decides which directories are allowed to take snapshots. And he can also say if a user can take the snapshot of the directory that he owns. Okay, so he can decide whether and then the number of snapshots that he wants to allow. Currently, you only support read-only snapshots. The architecture has been designed to do read-write snapshots. I'm not sure when we're going to be going to read-write snapshots. Okay, and it's a NameNode only operation. In fact, the data nodes have no knowledge of it at all, that there is a snapshot that's happened. The metadata in NameNode is kind of changed to do that. It's a very instantaneous creation, very fast to create a snapshot, and the change of memory that is used is proportional to the changes between the snapshots. If you take a snapshot, a second snapshot, and you're making no changes to your namespace, it doesn't cost you anything. As soon as you start making changes, it only costs you the delta that you have changed. Pretty typical in most systems that do that. Okay. The way we make snapshots available is very similar to what, for example, is in NetApp system. So you have path, and you could specify .snapshots, and it's a hidden directory. If you mention it, then underneath you can look at the snapshots. And so, for example, file.txt has a snapshot under its original path with a particular snapshot name. And one of the advantages of doing it like this is that we needed no special APIs to recover from your snapshot or for a user to access your snapshot. No new APIs, no new command lines. As long as you specify .snapshot, snapshot, and anywhere in the path, if that thing exists, it'll let you access it. Okay, so for example, you could recover your file with the little command that I showed you over there. Copy an important file that you missed, you can put it back into your path. Okay, and there then there are commands to create snapshots. These are more kind of operator commands. Okay, to create snapshots and to delete snapshots and to look at diffs between snapshots. Okay, but apart from that, no real changes. Okay. So I'm going to move to the next topic. A number of improvements in Hadoop. So we do checksums, and now that's been kind of improved. So we take about 3x less CPU than we used to. The read path now has significant improvements, less copies. So we, by the way, are implemented in Java, so you have to be more careful about copies and things like that. We have something called a short-circuit read. So basically, if your application is running and you happen to be on the same node where your data is stored, and that is actually the mode of operation Hadoop that your computation moves to where your data is, you no longer have to stream the data from your data node. So normally what happens is that the client reads and it gets streamed the data via a socket. And so now what happens is instead it reads the data directly. And the way we have done that is to use Unix socket domains. If you're local, we actually set up a connection between the client and the data node using Unix socket domains, and we check the permissions, etc., and we pass the open file descriptor. So it works really well and has given us significant improvements for random reads particularly, and that's more because the random read implementation in HDFS wasn't that efficient. Okay, but even on the other one, it has given significant improvements. The only thing ugly about this is that we are exposing this to our client-side library. So it's still hidden in the client-side library, but the fatter you make your client-side library, the worse it is down the road for you to have a portable client-side library. So right now, our client-side library is written in Java, and at some point we will write the client-side library in C and then have Java call C, so we maintain a single client-side library. Okay, but that's really the only ugly part. The other thing we have done is I/O improvements via POSIX fadvice. And one of the problems that occur in a system like Hadoop is because you've got huge amounts of data and you're processing huge amount of data, your buffer cache is typically useless. And the system is trying to put things in the buffer cache and trying to do it. So what we do is we use fadvice basically after a write to say that, don't bother caching this, or after read, when we do the read ahead, we do that. Okay. And so that's one of the changes that's actually improved our performance quite a bit. And so really it helps us more on the read ahead because Unix has very good read ahead when you're doing read. So it actually helps us there. So the buffer is much more effective. Okay, and then we've done some more, zero copies of libHDFS. So depending on what you're looking at, it's 2.5 to 5 times faster. Pretty much, very much close to getting to disk speeds. Okay, on reads and writes now. And lots of this improvement is significant, about 80–90% of the improvements have been backported to Hadoop 1. So you can get this on Hadoop 1 and 2. Okay. So we recently added another thing, NFS support. So it's a gateway, it's a set of daemons that allow NFS access. You can now use, mount it as a NFS file system. It does not support random writes. Okay, so you cannot do random writes, and you cannot also have multiple writers to the same file. That's a HDFS restrictions. It'll throw you an error code if you do that. But apart from that, it works really well. It does currently support NFS v3, which is actually the reason why we have to use gateway. The gateways are stateless. Okay, so there is no state on the gateways. Future work is going to be more on potentially high availability for NFS gateway, but the other thing is NFS v4 support. And I'm not an NFS v4 expert, but from what I understand, that you can actually redirect a client to a different location. And so if we do that, then we can actually get rid of the gateway completely. And so we will then have a client go to the name node to do an NF. There'll be a mini daemon in the name node. In fact, not even daemon, just threads in the same address space. And it'll actually redirect you to one of the data nodes to read from there. Okay? And so that is something that would basically mean that now your data will go directly from the specific data node that has the data. And that is something that we do for our REST protocol. So one thing that is important about our REST, we also have a REST protocol. Even in that one, we have a daemon inside each data node and name node, and so the name node redirects the REST protocol to the client nodes, and we'll be probably doing the same thing for NFS v4. Okay? So what also means that another big advantage, not just that your AI is going directly, that you have one mount point. Right now with the gateway, you have multiple mount points depending on how many gateway agents you use, which means the client needs to decide which mount point he uses, and that becomes how you scale your bandwidth. And really the client doesn't want to think that way. Okay? So that's an improvement that we'll be making. So wire protocols, this is maybe one of the things that has been embarrassing about Hadoop, that we did not have wire compatibility across different versions of Hadoop. So within the same release, Hadoop 1, 1.1, 1.2, all the dot releases had wire compatibility, and we switched to a measure release, again it would break it. And so for example, between release .18 and 1.9 and 2.0, 0.2, we used to break wire compatibility. Now we have used protocol buffers, and so we're going to be wire compatible from Hadoop 2 going forward, from 2 to 3. Of course, it will be 2 to 2.1, 2.2, 2.3, but even going from 2 to 3 to 4. Okay. It will also enable rolling upgrades. That currently you kind of have to upgrade the whole Hadoop system in one shot. We've also made, Hadoop actually has a very, very extensive security environment. It uses Kerberos and then uses its own tokens internally to supplement. And that now has some changes made in the negotiation phase of SASL in the protocol so that we can plug in other authentication mechanisms in there. So we plan to add things beyond Kerberos. So I already mentioned that we had, in Hadoop 1, we didn't really have append, so you could not append to the end of a file, and now you can. There are some other improvements in relationship to other projects. So for example, there's something that HPA is often used to notice that a node has gone dead. HDFS normally takes 10 minutes before it will declare a node to be dead. And clients automatically recover with dead nodes. In case of HPAs, the stale nodes that were still not marked as dead. So you introduce inside HDFS a notion of a stale node. So for example, when a node does not report from a certain point, then we put in a stale section, and so it will not be given out. Okay, and then it's something pretty obvious that we should have done. Other things is block placement enhancements. So for example, in the cloud, you have multiple VMs on the same node, and what you don't want to do is to put your replicas on the same physical box. And so that's another enhancement we've done for virtual machines and for cloud deployments, because in the cloud, virtual machines are typically used. Okay. Another big one is, and this comes mostly thanks to Java, we now have support for Windows, and that works pretty well. In fact, Hortonworks distributes for Microsoft HTTP, the same HTTP that we Hadoop development Hadoop distributed platform for, Hadoop data platform for both Linux and for Windows. Okay. Minor improvements, we now have file and block IDs, and this was partly done to do an NFS work, and will actually let us have improvements in improving for archival and things like that. Okay. So kind of looking summary of our enterprise, so storage fault tolerance, it's kind of been built into Hadoop from day one. And like I mentioned, the last study we did gave us over 7 nines. Since then, we fixed those bugs. We haven't seen any error. But we need to do a longer study to see how many blocks. But at Yahoo, for example, all the clusters have moved to Hadoop 2. Or since this bug was found in 2010, we haven't seen any corrupt blocks at all. Okay. High availability for the NameNode wasn't there. It's there both in 1 and 2. We have a whole bunch of standard interface. We have REST protocol, Fuse. Fuse is now going to be used less given that we have NFS. And then we have libraries for you to use on the client side. Wire protocol compatibility across major releases. Rolling upgrades are now possible because of wire compatibility that we maintain. Snapshots, disaster recovery. So we have a tool called DisCP. It's actually been there since 2007 when I joined Yahoo. This tool was there. So basically what it does a parallel copy of data across clusters, and it's been used both, by some of the major deployments to do copies across clusters. It does it in parallel. You can also specify how much bandwidth you want to use, because Hadoop can actually overwhelm your pipes because it does things in parallel. And so that's a tool that's been there for a long, long time. Okay, it does diffs off the two sides and then does copies it. Now, the thing about Hadoop, because all the namespace in memory, they're doing the diff is very fast. Okay, now with snapshots, we'll probably be doing a snapshot diff. Okay, and we are adding tools into our Ambari management platform for automated replication, etc. Okay, so now I'm going to spend a little bit of time on kind of futures. The big kind of change happening in Hadoop is that part of the ecosystem in Hadoop is moving from batch to real time. Okay, so much faster queries because of Stinger and Tez, and HQueries also tends to be more interactive usage. So what we have done is we have a Jira HDFS 2832 that basically changes and lets us take advantage of things like SSDs. So what happened was the data node does not distinguish between different kinds of storages. So it treats all the disks as uniform and reports the NameNode as one big pool. Now instead what it'll do is it'll recognize the different properties and then report that this block is sitting on a disk of the following property. Okay? And what that means is that at the NameNode level and our higher level APIs, we can start saying this data sits on this side of storage and then give you a choice where to put the data. So things like putting your data on SSDs, you could say I want this data on SSDs, for example. Okay. Of course, right now it might accidentally be on an SSD if you plug it in. Okay. You could also say we'll be adding things like I want one copy on an SSD, the other not on an SSD, because SSDs are going to stay pricey for quite a while. Okay. We also are treating RAM as also a storage kind of thing. So we also report data that is on the RAM that way, and so we're using that to do caching. So there is actually work going on doing cache and keep data in memory, keep files in memory. And so, for example, you might have dimension tables that you want to keep in memory because they're widely used in queries, and you'll be able to do that. The initial version, basically, you have to specifically say, I want to pin this dimension table, and the system will pin them into memory. And it uses mmap and mlock to do that. Down the road, we'll be caching more partial amounts of data that are hot and using LRU caches and things like that. Okay, so right now it is pretty simplistic there. As I mentioned, the kind of areas that is making some fundamental storage abstraction, the data node becoming a block access pattern is a major change that will actually give us a lot of innovation down the road. As I mentioned, the heterogeneous storage, block level APIs so that you can now access the data nodes directly, granular placement of blocks. Longer term, we want to put a key value store in Hadoop. And so a block level access means that we could build that independent of the HDFS namespace but use the same block storage. Okay. Another thing that people are looking at is to be able to serve structured data directly from the data node. So for example, for it to understand file formats and the main two motivations for that. One is to give column level security. Second one is to allow third-party parallel databases to access the data with a very thin protocol. So that is something that we are considering in the kind of medium term. So the other big change is on higher scalability. Let me kind of go to the next slide. And I'm not sure this slide actually does justice to the idea. The idea is to now think of a NameNode not as a single volume, but multiple volumes. Okay, and so we want to start moving, management policies like quota to volume rather than directory level. And of course, as before, you'll be able to mount them into a mount table, either within the server or across. But what starts becoming more interesting is when we only store the working set in memory. Once we only store the working set in memory, then you can store a larger number of volumes, significantly larger. So right now you can store about 400 million files with about 60 to 80 gigabytes on the NameNode RAM. Okay, you could go higher because RAM is not that expensive. But with this thing, you'll be able to store about 2 billion, 10 billion files. And so the general idea is you keep your working set in memory, okay? And then what happens is that the number of name nodes that you have on the top, the number of data nodes that you have on the bottom is tied to how much IO bandwidth you want and how much physical storage you want. Number of name nodes you want to have on the top is how much namespace working set you want to keep in memory, because the more namespace working set you keep in memory, okay, the more applications you can run that are using old data, new data, etc. Second thing is the number of operations you want on the name node. Okay, right now, for example, a name node can serve about 100,000 concurrent clients in a Hadoop cluster. Okay, and so we haven't seen issues that, for example, in the big clusters at Yahoo, we haven't seen issues there. Okay, but that's what's going to happen is that you will have a set of name servers and you will have to move volumes back and forth quite easily. Okay, you still won't be able to do a rename across volumes. But the other advantage that starts coming as a side effect is you can start having n plus k failover. Right now, each volume requires its own failover guy, right? With something like this, I can failover a volume to another one. Okay, so I could do a failover within my set of n name nodes, or I could have n plus k failover where I have k guys on the side and do failover that way. That is not possible today. And so that will become possible because of this. Okay, in high availability, we want to actually, I would like to get rid of the journal nodes and move the journal straight into the data nodes themselves. So the journal is stored in data nodes. Main issue there is journals need to have predictable latency. They don't need to have super low latency, but they need, because of batching, but they need predictable latency. And that is the challenge because the data nodes are also being bombarded with regular clients. So that's something we want to move there. Okay. Of course, on our full stack stuff, you want to start doing other services. Okay, so kind of, myths, misinformation. Hadoop was not reliable because, it stores its namespace in memory. That wasn't true even a version 0.01 of Hadoop. Okay, it was just never true. It started to get used for production kind of use at Yahoo in 2006, 2007. Okay, when NameNode dies, state is lost. Like I said, that never ever was true. One of our competitors, a non-open source company, says that even though they know it's not true. Does not support disaster recovery. We used to have this CP in 2007. Okay, hard to operate for newcomers. That was true. There's a lot more improved usage for installing using Hadoop. Performance improvements. This is always going to be ongoing. Okay, NameNode as a single point of failure that's been fixed both in Hadoop 1 and 2. NFS, for example, is now there. Snapshots are now there. So that kind of covers my my talk. Questions?
Are the snapshots going to be accessible through the REST API as well?
Yes. So the thing about snapshots is because they're part of the path name, you can access them via any of the APIs. In fact, we didn't have to do any work to make it available.
What's the primary use case for NFS? Is it just convenience, or is it ingest, or?
No, it's actually convenience. I mean, there is a. And when somebody starts using the demo of dragging a file onto Hadoop, You don't ever do that in production because you drag it through your laptop, right? If you check it, right? So it's kind of a silly thing to have data that you drag off the laptop. Okay, so it's mostly for things like that. A good one is, so for example, if you had your database and you wanted to dump your database, there's something called scoop. Okay, but now what is actually much better for databases is to do a dump onto the local file. Okay, and then actually drag it off onto an NFS mount. And to manage that from outside Hadoop, you could just do that. Okay, so that has been the primary. I think if you were to add random, writes, of course, that would change the whole equation, right? People would start using Hadoop as an NFS file system. But if your application isn't doing random writes, you could start actually using Hadoop as a cheaper NFS file system. I don't know if that's what happened or not. Other questions? Either you understood everything I said, or you got bored to death. Or you already knew all this anyway. Okay, thank you very much.